Let's consider the graph of the function f(x) on the closed interval ab, including ab. It's a closed interval. It is including the endpoints a and b. So here is a and b. And if I would like to consider the function only on the closed interval ab, I really do not care about this part, and I do not care about this part. We easily observe that the green dot is the lowest point on the graph of the function between a and b. This is the absolute minimum of the function on the closed interval ab. We also observe that the blue point is the highest point of the graph of the function on the closed interval ab. This is the absolute maximum on the closed interval ab. Let's observe even more. What are those 2 points, the lowest one and the highest one, compared with the other points on the graph? If you look at this point, this is also a local maximum on the graph of the function y equals f(x). And this point is also a local minimum. Now we are going to change the closed interval ab. Let's now take this. So I do not care about that, and I do not care about that. This is the lowest point of the graph of the function on the closed interval ab. So this has to be the absolute minimum of the function on the closed interval ab. This point, exactly as before, it's the highest point of the graph of the function on the closed interval ab. It is absolute maximum on the closed interval ab. Now again, we would like to observe what are those points with respect to everything. If you observe, this is a local maximum, and this one is an endpoint of the closed interval ab. This is exactly the value at which x equals b. Now we're going again to change the interval ab. Let's observe. Again, we don't care about this and this. This is definitely the absolute maximum of the function on the closed interval ab. And this is clearly the lowest point on the graph y equals f(x) on the closed interval ab. So this is the absolute minimum on the closed interval ab. Now let's do as before. Let's relate now those 2 points to the whole graph. This is the endpoint, if you can see. It's the point where x equals a. And this one is also an endpoint. This is the point at which x equals b. We observed that the absolute maximum and minimum of a continuous function on a closed interval occur at the following points. It can be a local max, local mean, or one of the endpoints of the interval ab, or both of the endpoints of the interval ab, which mean a and b. But the question is even more. If you observe, we always have an absolute max and an absolute mean for the function on the closed interval ab. And this is indeed always true. This is a theorem. If f is a continuous function on a closed interval ab, then f attains an absolute maximum and an absolute minimum on the closed interval ab. In other words, if f is a continuous function on a closed interval ab, then first, f has at least one value c on the interval ab, including ab, such that fc is the absolute maximum of the function f on the closed interval ab. And second, f has at least one value d on the closed interval ab, such that f of d is the absolute minimum of the function on the closed interval ab. We observe that all absolute maximum and minimum of continuous function on a closed interval occurs at local max and min, which means critical numbers, or at the endpoints a, b. So here are the two specific values of x that we should suspect maybe there is an absolute maximum or minimum at. So to find the absolute maximum and minimum of a continuous function on a closed interval ab, we need to do two things. Step 1, we have to find all the critical numbers of the function on the closed interval ab, because each one of those values of x is a suspicious value for which the function attains absolute max or min. But also, we need to evaluate now the value of the function at all critical numbers from 1 and at the endpoints a and b, because also the endpoints are suspicious values of the x's at which f of x attains absolute max or min. And in step 3, obviously, well, the largest value of f is the absolute maximum, and the smallest value of f is the absolute minimum. Example, find the absolute extremes of the function fx equals 3x to the power of 2 plus 3x minus 5 on the closed interval negative 2, 3. fx is a polynomial, it is continuous function, it's also a differentiable function, so we have to check all the critical numbers on the interval, negative 2, 3, and we have to check at the endpoints. In step 1, we first would like to find all the critical numbers on the closed interval negative 2, 3. We differentiate the function and we solve that for 0. We get that x equals negative 1 over 2, which is definitely between negative 2 and 3. In step 2, we are going to evaluate, and I will use a chart. We have one critical number and two endpoints. We are going to substitute the values of negative 1/2, negative 2, and 3 in the function fx. Here we get minus 23 over 4. Here we get 1. And here we get 31. In step 3, we have really to compare those numbers. This is the only negative number, and this is the highest positive number of the two numbers that are positive. So we can conclude that the absolute maximum is 31 and the absolute minimum is minus 23 over 4. Another example. Find the absolute minimum of the function fx equals e to the x times cosine x on the closed interval 0 pi over 2. Please pay attention. Fx is a product of two continuous and differentiable everywhere functions, e to the x, which is an exponential function, and the cosine function cosine x. As a result, we know that fx is continuous everywhere, and again we have to find critical numbers on the interval, and we have to evaluate the critical numbers, endpoints, and find the absolute max and min. So we will start with step 1, critical numbers. We differentiate the function. Let's write as product of terms. And I want this to be 0. This one is never 0, it's always positive. This one can be 0, and I have to solve that. It means that cosine x equals sine of x. It means that tangent x equals 1. And because the closed interval is between 0 and pi over 2, there's only one solution, and this is x equals pi over 4. Step 2. Let's fill in the chart. We have one critical number, pi over 4, and two endpoints, 0 and pi over 2. We are going now to substitute for the x. Here we get that. At 0 we get 1. And here we get 0 because cosine of pi over 2 is 0. Let's read the question again. We have to find absolute minimum, so we need the absolute minimum only. I observe first of all that the first two numbers are positive, and the third one at pi over 2 is 0, which is definitely the smallest number of all those numbers here. As a result, I can see immediately that the absolute minimum is 0. Example. Here is the piecewise function f(x), which equals 2x to the power of 2 plus 2x when x is less or equals to 2, and 2x cubed when x is more than 2. 1. Explain why the function must attain absolute maximum and minimum on any closed interval. 2. Find absolute minimum and maximum of the function on the closed interval -2, 5. 1. Pretty clear. F is continuous, except maybe at x equals 2. Each one of the pieces of the piecewise function f(x) is just a polynomial which is continuous everywhere. The only suspicious point at which this function may be not continuous is only at the point where x equals 2. So we can check that. The limit from the right is 8. The limit from the left is 8. And f of 2 is 8. So we can conclude that f(x) is continuous everywhere, including x equals 2. And because of that, there is a theorem that says that if a function is continuous on a closed interval, then it must attain absolute max and mean on this closed interval. But f is continuous everywhere, so it is continuous on any closed interval. We can conclude then that f must attain absolute max and mean on any closed interval, including the closed interval -2, 5, which is what we're going to do now. First, we have to find critical numbers. We're going to differentiate that as a piecewise function first. We cannot include x equals 2 because this needs to be checked. So the derivative when x is not 2 is 2x plus 2 when x is less than 2, and 3x to the power of 2 when x is more than 2. And we want each one of those first to be 0. This is 0 when x is -1. You have to check that this is in the domain at which x is less than 2. It is. And this is 0 when x equals 0. But the domain of this branch is when x is more than 2. So x equals to 0 cannot be a critical number of that. And we get from here the critical number x equals -1. But this is not enough. We also have to check at x equals 2. The function is continued at x equals 2, but I would like to recall all those critical numbers for which the function is not differentiable. So let's see if the function is differentiable at x equals 2. It may have a sharp corner, and it may be not differentiable at x equals 2. We have to check that. We are checking now to see if x equals 2 is another critical number. We differentiate the function from the right side of 2, and we get 3 times x to the power of 2, plug 2 for the x, and we get 12. Now we differentiate from the left side of 2. And it is 2x plus 2 when x equals 2, and we get 6. There is a sharp corner. It's not differentiable at x equals 2. So how many critical numbers this function has? First, x equals -1, and then x equals 2. Let's do the chart now. We have to evaluate the function at the two critical numbers and at the two endpoints. Be careful, it's a piecewise function. Make sure you put the right x at the right branch of the function. F equals 2. F equals -2. If you noticed, all of these are using the branch that f of x equals x to the power of 2 plus 2x. But when x equals 5, we have to use the x cubed. And we get this. So in the step now, we just have to figure out which one of the values is the lowest and which one is the highest. Pretty easy to see that this is the absolute minimum, and this is definitely the absolute maximum.